Introduction to nuclear chemistry. Nuclear chemistry studies atomic nuclei and their transformations, including radioactivity and nuclear reactions like fission and fusion. This field of chemistry focuses on atomic-specific reactions and processes. Unlike regular chemistry, which primarily deals with electron interaction, these processes release energy for applications like nuclear power generation and medical treatments. Understanding nuclear processes is crucial for technology, healthcare, and our understanding of the universe.
How nuclear reaction takes place. Nuclear chemistry reactions involve changes in the nucleus of an atom. Unlike regular chemical reactions that involve electrons, in nuclear reactions, the number of protons and neutrons in the nucleus can change, leading to the transformation of one element into another. This can happen through processes like fission and where a huge nucleus splits into smaller nuclei, or fusion, where light nuclei combine to form a heavier nucleus. These reactions release or absorb a significant amount of energy and can also emit particles such as neutrons, protons, or electrons in the form of beta decay. How nuclear chemistry is used in space exploration. Space nuclear propulsion refers to the use of nuclear reactions to generate thrust for spacecraft. This technology harnesses the energy released during nuclear fission or fusion to propel vehicles in space, offering advantages over conventional chemical propulsion systems. Nuclear propulsion systems can also operate for longer times, making it the most ideal form of travel. The two types of nuclear propulsions. Nuclear thermal propulsion. This is a type of thermal rocket that uses the heat from a nuclear reaction. In a nuclear thermal rocket, a working fluid, typically liquid hydrogen, is heated to extremely high temperatures in a nuclear reactor and then expands through a rocket nozzle to create a thrust, which will be elaborated more in the next slide. Nuclear electric propulsion. This is a type of spacecraft where thermal energy from a nuclear reactor is converted to electrical energy, which is used for spacecraft propulsion technology. How nuclear propulsion systems work. First, a liquid propellant like liquefied hydrogen is pumped through the reactor core, which is heated at extremely high temperatures, splitting the atoms, creating heat. The core contains uranium-235 atoms. A neutron is absorbed by a U-235 nucleus. The nucleus becomes unstable and splits into two smaller nuclei, releasing typically two neutrons, usually elements like barium and krypton. This also usually emits fusion fragments, gamma rays, and heat. Second, the heated propellant expands into a gas, which is then forced out of the rocket nozzle. Third, the hot hydrogen expands and is expelled out of a nozzle at high speed, creating thrust that pushes the spacecraft forward, which is shown to the right of the powers. When this increase of high temperature takes place, this causes the hydrogen gas to expand rapidly. Some hydrogen molecules may ionize, splitting the protons and electrons. The hot high-speed hydrogen gas, including H2, H+, and electrons, is expelled through a nozzle. This generates the thrust, propelling the spaceship forward. Some gamma rays may pass through the reactor material and need to be managed to protect the spacecraft. Dense materials like lead or specialized composites are used to shield against gamma rays. Shield is strategically placed around the reactor to absorb gamma rays. This is important as it protects the crew and the electronics from any harmful rays that can affect the spacecraft. Now, once the nuclear reaction occurs in the spacecraft, it generates heat or electricity that is used to produce thrust, enabling the spacecraft to travel through space more efficiently. The specific outcomes and considerations depend on whether the spacecraft uses nuclear thermal or electric propulsion. The benefits of nuclear chemistry on space exploration. Nuclear reactions release millions of times more energy than chemical reactions, making them very powerful. Nuclear thermal propulsion could allow for more flexible abort scenarios, allowing crew to return to Earth at multiple times if needed, including immediately upon arrival at Mars. This makes nuclear propulsion a cleaner option for long-term exploration and sustainability.